Welcome to the Q&A session 15 from the playlist of Wave Optics. The topic is the bright and the dark fringes. And this session is in continuation of the session number 12, in which we have studied about the bright and the dark fringes. And we have also calculated the distance of the nth bright fringe and the nth dark fringe from the center of the screen, or you can say from the central bright fringe. So the question here is, in a Young's double slit experiment, the slits are 0.5 mm apart, and it is found that the ninth bright fringe on one side of the central bright fringe is at a distance of 10.5 mm from the second dark fringe lying on the opposite side of the central bright fringe. Here the interference pattern is observed on a screen which is 100 centimeter away from the slits. So the wavelength of the light used is, so this is what we have to find. Now in the session number 12 we have seen that the distance of the nth bright fringe from the center of the screen, or you can say from the central bright fringe, is given by, say, this is xn, this is equal to n lambda d upon d, where d is the separation between the slits and d is the distance between the screen. Lambda is the wavelength and this is the nth bright fringe. So in this case, the ninth bright fringe can be written as, let's say, x9, and since this is a bright fringe, so I am writing it here as b. So ninth bright fringe will be equal to 9 lambda d upon d. Now here the ninth bright fringe which is lying on one side of the central bright fringe is at a distance of 10.5 mm from the second dark fringe which is lying on the other or the opposite side of the central bright fringe. So let us say the second dark fringe is equal to x2d. So this x2d is the second dark fringe, and this will be equal to 2n minus 1 lambda d upon 2d. So this is the formula for the nth dark fringe from the center of the screen, or you can say from the central bright fringe. So x2d will be equal to, here n is equal to 2, so 2 into 2 is equal to 4, 4 minus 1 3, so this is equal to 3 lambda d divided by 2d. Now it is found that the ninth bright fringe on one side of the central bright fringe is at a distance of 10.5 millimeter from the second dark fringe which is lying on the opposite side of the central bright fringe. So here 10.5 mm will be equal to x 9b plus x 2d, because here the bright fringe is lying on the opposite side, or you can say that here the this ninth bright fringe is lying on one side of the central bright fringe, and the second dark fringe is lying on the opposite side of the this central bright fringe. So because of that, this 10.5 mm, which is the distance between these two fringes, this will be equal to x9b plus x2d. So this can be written as 10.5 into 10 to the power minus 3 meters, and this can be written, now from here if I add these two, so here lambda d by d is common, so lambda d by d is common, and in bracket it will be 9 plus 3 by 2. So here 10.5 into 10 to the power minus 3 is equal to, now lambda is something which we have to find because this is the wavelength. D is 100 centimeter because this D is the is the distance between the two screens. So this is 100 centimeters. So this, if I am converting this into meters, so this will be equal to 1. And D is the separation between the slits. So this is equal to 0.5 mm. So this can be written as 0.5 into 10 to the power minus 3 into, this is, if I take the LCM, this will be equal to 9 to 18 plus 3, that is equal to 21 by 2. So from here, this 10.5 can be written as 21 by 2 into 10 to the power minus 3. This 0.5 into 10 to the power 3 minus 3 can be taken on the left hand side of this equation. So this will be equal to 0.5 into 10 to the power minus 3, and this will be equal to lambda into 21 by 2. So from this, 21 by 2 and 21 by 2 is getting cancelled out. So from here, the value of lambda is equal to 0.5, or you can say 5 by 10 into 10 to the power minus 6, or this is equal to 5 into 10 to the power minus 7 meters. So this is the wavelength of the light. Now, this wavelength of the light can be also written in terms of angstrom. So now we know that 1 angstrom is equal to 10 to the power minus 10 meters. So I will be converting this value as 5 into 10 to the power minus 7 into 1000. Means this wavelength can be also written, this wavelength, that is 5 into 10 to the power minus 7 meter, can also be written like this. So this is equal to 5 by, this is 5 into 1000, this is equal to 5000 into 10 to the power minus 7 into 10 to the power minus 3, this is equal to 10 to the power minus 10 meters. Or this is equal to 5000 angstrom. So the wavelength of the light which is used in this experiment is equal to 5000 angstrom, or simply we can also say that the wavelength of the light is equal to 5 into 10 to the power minus 7 meter. So thank you very much for joining this session. In the next session, I will be taking up a different topic from this chapter of wave optics. So till then, have a nice day. Bye.